Hello and welcome to my project. I'm Thomas Matthews and this is my ASL alphabet bot. My desired outcome was to create a cheap biomimetic robotic hand to be used as an engaging educational tool to teach adults and children how to sign the alphabet in American Sign Language, helping to bridge communication issues that arise with the inability to hear speech. The motivation for this was that 70 million people worldwide suffer with some form of deafness. American Sign Language, ASL, is the most common sign language worldwide. However, only 250,000 people know how to sign American Sign Language. 80% of deaf people are in developing countries and have little means of learning any form of sign language, and this can lead to difficulty with communication, which would then lead to isolation and feelings of loneliness as people cannot communicate properly with others. Here we have two existing robotic hands that I drew inspiration from. On the left we have the highly biomimetic anthropomorphic robotic hand. This system focuses on realistic movements and dexterity achieved through a series of complex artificial tendons. This robot is extremely advanced and highly unobtainable for this project. However, it gave me an indication of what's possible. Continuing with the tendon-based designs, on the right is the Shadow Robotics dexterous hand. This hand is less biomimetic in design and focuses more on manipulation of objects rather than human-like movements. However, its more obtainable components and construction materials made it the main focus of my research, with my goal being a hand that sits somewhere in between these two designs. For this project I had four main aims. My first aim was to follow a biomimetic approach to the design process. This would allow for a more accurate recreation of the human hand in both size and proportions, as well as movement and dexterity. The second aim was to create a hand with high levels of dexterity and control, as a means of accurately recreating the signs. I also wanted to create a software capable of splitting inputted words into individual letters and returning the corresponding sign for the hand to recreate. My final aim was to create a fully functioning system that could accurately and reliably translate words letter by letter into ASL. To better understand my design choices, we must first understand the anatomy and range of movement of the human hand. Starting with the fingers, a complex series of tendons within the fingers and hand allow for two types of movement. Firstly, flexion/extension. This is the opening and closing of the fingers, with a range of 80 to 120 degrees of motion in each of the three joints. Secondly, abduction/adduction. This is the horizontal spreading of your fingers, with a range of 20 to 25 degrees of motion. The first joint, the MCP joint, can also move independently of the second two joints, the PIP and DIP joints. Achieving my final finger design took many iterations. However, to best mimic the movement of a human finger, I decided to use fishing wire as artificial tendons, allowing for more realistic movements and reducing weight and size of the finger as the motors could be placed outside of the hand. However, my first designs were controlled by two lengths of wire connected to only one motor. 90 degrees in one direction would control the flexion, and 90 degrees in the other would control the contraction of the finger. However, the wire would often collect at the joints and rarely return the finger to its starting position. To fix this issue, within my final design, the motor was used to only control the flexion of the finger, allowing for greater control as the full 180 degrees of rotation could now be used solely for flexion. And to return the finger to its resting position, a length of elastic was added to the back of the bones and stoppers were also added to prevent hyperextension. To allow for the individual control of the MCP joint, I widened the first phalanges to allow for the tendon controlling the top two joints to run perpendicular to the axle of the MCP joint. And finally, to reduce friction, bearings and washers were added between the joints in my final design. To allow for the abduction of each finger, I originally designed a simple hinge joint with stoppers to prevent hyperextension. However, these stoppers were weak and prone to breaks, and the whole design was very unstable, with only 10 degrees of abduction in one direction, not the 20 degrees in both that I wanted. To increase stability, within the next design, I added a housing to the joint, which worked, but at the cost of added friction. To negate this issue, in my next and final design, I hollowed out the housing and allowed for movement in both directions. Here we have a short animation showing the two types of movement within the finger and the separate control of the MCP joint. The human thumb contains one of the most complex joints in the human body, the CMC joint. This joint, which can be controlled independently of the MCP and IP joints of the thumb, allows for movements in three planes: flexion/extension, abduction/adduction, and opposition/reposition, the thumb's ability to touch each fingertip independently. Much like the finger, these joints have a flexion of 90 degrees, but a large abduction at 60 degrees, and a small rotation of up to 20 degrees. To best recreate the complex CMC joint of the thumb, I began with a simple universal joint to allow for both flexion and abduction. My first design, however, was large and ineffective as the joint housing created high levels of friction. To tackle this, I removed the housing and decreased the size of the overall joint. This allowed for easier movement, and the smaller design increased the range of motion. I chose to remove the thumb's rotational ability as it was deemed too difficult and not necessary for the task. Much like the fingers, washers, bearings and elastic was added to the final design, and a cutout within the universal joint was added to allow the tendon controlling the top two joints to feed directly into the hand itself, minimizing any unwanted interference that would occur as the thumb moved. Here we have an animation showing the three different types of movement the hand can perform. Obviously the movements can be used together, however this is just showing them individually. The human wrist consists of a series of small bones called the carpal bones, which in conjunction with the ulnar and radius bones of the forearm allows for 50 to 90 degrees of flexion, 30 to 90 degrees of extension, 15 degrees of deviation in each direction. Deviation is the sideways waving motion of the hand. And finally, the ability to rotate your palm 180 degrees. This is called pronation/supination. For my robot, I wanted to focus on the flexion and rotation of the wrist as deviation was deemed too difficult to implement. My first design used a simple hinge joint and a set of gears in the forearm to allow for these movements. However, the hinge would massively affect the tendons within the hand when bending, causing the hand to close, and the set of gears not only caused the tendons to tangle, but also pushed the hand from the forearm itself. To reduce the tension caused by a hinge joint, I decided to use a 4-bar linkage for the flexion of the wrist in my final design. This was chosen because the centres of the top and bottom plate of the linkage deviate less when rotating, allowing for the tendons to run through the centre with little interference. I decided to move the rotating movement of the wrist to the base of the forearm, much like a human hand, as this prevents any twisting of the tendons. Here we have a short animation of the flexion as well as the twisting of the wrist. Moving on to the software, this was very simple as I wanted a hardware-based project. You simply type your word into the serial input and it splits the array up into individual letters for the hand to then perform the corresponding movements to produce the sign. Here we have a video of the hand signing the alphabet from A to Z. Each sign is held for 3 seconds to allow the user enough time to easily follow. Any word can be spelt out, as well as the numbers from 0 through to 9. But as you can see, not all the signs are perfect. The occasional joint gets caught, and the lack of a deviation motion in the wrist means the signs for G and H are in the wrong orientation. To conclude, I believe the project was successful. The hand can recreate most of the signs accurately and reliably. However, the lack of a deviation motion within the wrist prevents some of the signs from being recreated correctly. Taking this project further, the obvious addition of a deviation motion to the wrist would allow for more accurate signs. I'd also like to add full word translation and a form of text-to-speech to allow users to say words they wish to translate. Thank you so much for watching.